Hello, today I'm going to be speaking about the antiderivative integrals. So where does this symbol of the integral come from? It comes from the Greek letter sigma. To me it doesn't look anything like it, but apparently it does. And this Greek letter summa means sum. So let's say a sum of some natural numbers like 1 plus 2 plus 3 all the way to 100. This is how we would denote the sum. We're just saying how much 1 plus 2 plus 3 plus all these numbers all the way up to 100 is. So essentially what we're doing here is we're doing kind of the same thing. We're summing the areas of our rectangles underneath our graph to find out the area underneath our graph. And what do we have here? This is dx. The width of my rectangle is 0.3. So my dx is 0.3. And the length of my rectangle is L. This is the overlapping area. This is the extra area I don't need. So I'm going to have an approximation. I'm going to have more area than I actually have underneath this graph. That is not good. But let me show you how we calculate the area first. So we're going to do the simple calculation for a rectangle, which is a times b. Our a is going to be dx. Our b is going to be L, the length of our rectangle. We can tell that by certain input and output values of our function. Okay, what happens when our dx is arbitrarily small, 0.01? The overlapping area is smaller, as you can see, and we're going to get closer to the truth, closer to the actual area underneath our graph. Now, if dx is going to get really small, then we can say that our approximation is going to be quite precise. So what we want is dx to be as small as possible, and we get the very precise, you could say almost infinitely precise, area underneath our graph. Okay, now there are some different methods for integration. First one is plug and chug. So you have these huge tables. Some of them you have to memorize them, like, let's be honest here. It's good if you can derive some of the equations. So like, for instance, you can derive this one quite easily. Essentially, you're taking a step back. So if I derive x to the power of 4th, I get 4 times x to the power of 3 from the tables of derivatives, or you can derive this as well. Or you can check out my videos on how to derive this. I've done something similar with x squared. Essentially, what we are doing here, if I integrate 4x to the power of 3 dx, what will I get? I will get x to the power of 4 over 4 times 4, which is x to the power of 4. So I'm getting back to my derivative. So it's kind of going back and forth, really. It's the antiderivative. It's the step before I derive my function. So you can derive this quite easily. And so x to the power of n dx equals, dx is a really small number. It's our argument. It's the argument of our function. X to the power of n equals x to the power of n plus 1 divided by n plus 1 plus c, some constant. Now, why is c important? Let's say we just have dx, we get x plus c, because x to the power of 0, x to the power of 0 plus 1 is x to the power of 1, 0 plus 1 is 1. Let's say we have a function like 2x plus 2. When we derive a constant in our function, it goes to 0. So if we derive this, we just get 2. If we integrate 2 dx, we just get 2x without plus 2. So that's why we have to keep the constant value, plus 2. Otherwise we would have a completely different function, which we don't want. Now, the second method I want to mention is substitution. When do we substitute? We substitute when we don't know how to integrate our function. We can't just plug and chug based on our tables that we've memorized or derived. What we do is we try and make this simpler. We try and make life simpler for us. So we find something it could be close to. Do you see what it's close to? I urge you to pause the video and try and work through this by yourself. If you can't, then just follow me. So we are going to substitute, and our u is going to be equal to 2x minus 1. We are going to derive this. We are going to get du and 2 times dx. Dx is going to be equal to 2u du over 2, sorry. So we know what dx is equal to, and we know that we can substitute this as something we know. So like similar to x to the power of 5, let's say. So that would be x to the power of 6 divided by 6. We're trying to make things simpler for us. We're trying to find something that looks like something from our tables. So we're going to get the integral of u to the power of 5 divided by 2 du. Again, dx is equal to du by 2 over 2. That is equal to u to the power of 6, so 5 plus 1, divided by 5 plus 1, which is 6, times 2, which is 12, plus some constant c. We mustn't forget this, otherwise we get a different function. We see what u is equal to, 2x minus 1 to the power of 6 divided by 12 plus c. How do you know this is the right result? Just derive it. Derive it again and see if it gives you this. Now, what we are going to do is I'm going to show you a method that is used quite often. In English it means by parts, in Latin it's per partes. Let's say I'm just going to make up an example. We have the function x times cosine of x. So, what we don't want is to make life complicated for us. We couldn't solve this integral in another way. Let me just show you the how we solve per partes. So we derive one of the functions, then we have the two functions that are not derived, then we subtract them, and one of the other functions is derived. You can switch this, so this can be derived and this can be derived. Obviously it depends on the case. It depends which one is better for you guys. So what I'm going to do is I'm going to choose the easier path. So again, I'm going to write my integral here. X times cosine of x dx equals. So if we say that this one is derived, let's say that our x is derived, then before our x would be what? Again, look at your table or derive it. Be x squared divided by 2. If we have fractions everywhere and we just make the whole place a mess, that's not really what we want. You don't really want to be working with functions. It's going to make your life like hell. So this is stupid. So we're going to do this. We're going to say that this is our x not derived, and once we derive it, it is equal to 1. Now, which one of these is easier to work with? I would say this one, this part. You could do the integral like this, but it's stupid. So our derived function here has to be then cosine of x. So let's say cosine of x is derived. And before it was derived, it was minus sine of x. I urge you to derive this for yourself. The integral for this and also, well, I mean the derivative for this. What is the derivative of cosine? What's the derivative of sine? So we're going to put, based on our formula, we're going to put the functions in before they were derived. So x times minus sine of x. You could just put that in front, it's up to you. And then the integral of 1, because now our x is going to have to be derived, because here cosine was derived. So 1 times minus sine of x dx. What can we do with minus sine of x? We can put the minus sign in front. So what we'll get is minus x times the sine of x plus the integral of sine x. So it was sine before it was derived, dx. It was minus x times sine of x plus cosine of x, and don't forget it, the constant c. And that is our result. We have some more advanced techniques on how to do integrals, which involve sort of substituting using a triangle. You could say there's you'd also solve some integrals if some integrals have a quadratic equation and it cannot be solved for real numbers. You can solve it in complex numbers, and there are some more advanced methods obviously on how to solve integrals, which I'm not going to go over now. And yeah, that's all for today. I hope you enjoyed the video. Please like, comment, share and subscribe, and don't forget to support me on Patreon for my up and coming linear algebra series. Thank you and see you next time.